Oh, the light. That's what I was going to do. Okay. I can't believe we have 4 classes after this one. It's madness.
Really?
The semester's almost over.
Only 4?
Yeah. We only have 2 weeks after this week, right?
Holy moly.
I don't think
right.
so.
I think
And then
it's-
finals. And then finals week.
Yeah.
Because that's the last week of April, right? Let's take a look at that.
Yeah, that's right.
2 more full, not even full weeks if you meet on Fridays.
Well, yeah.
Yeah,
Wait, are
for
we getting
us.
a Monday off on Easter?
No,
We get Friday.
Good Friday.
It's the
Sorry.
reverse.
Oh, well, it makes more sense for it to be Monday because Easter's Sunday, and so if you're like traveling,
But Good
But
Friday's
Good
an
Friday's a
actual
holiday.
holiday.
Wait, what? What was the response?
Good Friday is an actual holiday.
But it's
Oh.
actually,
Like
Yeah.
the Monday after Easter isn't like an actual day.
True.
like in the church, like Friday is way more important than Easter Monday.
Really? So
Because Good Friday is when Jesus dies.
that's okay. And then Easter's when it comes out.
Yes.
Okay. Yeah.
Yeah. When he comes out.
Got it. Okay. Oh God. These are the pants my wife told me not to wear. She like usually gives me the once over before I leave the house. She's like, "You've got stuff all over the front of you. You can't wear that." All right. Hi, friends. Howdy. Let's take a few minutes to settle in. Very simple today. Just focusing on the breath. Letting your breath do what it wants to do. Watching all the symptoms of breathing. Can you follow an entire breath from the moment it starts till the moment it ends? You can notice that you don't have to do anything to breathe. It's just happening. Maybe inside, make a smile. Or on your face, make one too. Think of something you are grateful for. Let's start some real analysis. Super grateful to be here with all of you. This is the last time I'm going to be teaching real for like, I don't know, till ever Cybert gives it back to me. We're the only 2 that ever teach it. Like, we love it. And so it's always a fight. It's like, yeah, I hold on to it as long as I can because it literally is my favorite class to teach here. It's my specialty. It's not his specialty, so I always feel like I got like a special claim on it as well. Not that he's an amazing mathematician, really brilliant man. So he can do anything. Alrighty. Oh wow, notes and stuff. Yeah. Do you all have any questions? There's a homework that would be. Oh, you do. Yay. That would be great to maybe turn in on Monday. And I suspect there will be only one more homework. Given that our homeworks span whatever time they need. And the last one will be a little larger than normal because it'll be like the final homework assignment. And I might actually even put a few things on there that you'll have to chase down yourself. Just like a concept. I always like doing that for the final thing. Like teach yourself this, read the book, we can talk about it, right? But demonstrating that you can understand math, because that's all that matters. When you leave here, nobody around to consult with, right? And you're on your own, out in the wild, wild, woolly world of whatever you go do. Kayla, my friend, what do you want to talk about?
425, B, C, and possibly D.
Okay, cool. Did I assign all those?
Yes.
Yeah.
Yeah. You assigned 4, 2, 3, A, and B.
And then I assigned 4, 2, okay, I'm not going to keep saying it so you can keep telling me yes.
4, 2, 2?
4, 2, 2.
4, 3, 2 is
Yeah.
the other one that was AD.
Wow, I didn't really mean to do all those. But since you've already done, have you done them all?
I mean, I've done scratch work. I'm really not sure necessarily that it's correct, but
Okay.
I did the work.
So I didn't assign A?
You did.
Okay, thank God. I was like
No,
the
you
easiest
assigned
one I
all
didn't
of
assign.
them.
No.
I just signed all of them.
Yeah. I just don't have a question on A. Because we
Okay.
did an example like that in class.
How about we don't have to do B, since I kind of essentially did that when I showed
Okay.
the continuity of x cubed.
Okay.
So if you've already done it, you can turn it in for like bonus points or something like that. So I'm not gonna diminish the work you've already done, but yeah, B is something that I kind of almost did, I think maybe last Wednesday.
Yeah.
So let's take a look at so C is still kind of, you're not quite sure about C. Let's take a look at it. How about we look at something like C?
Okay.
So I can show you how I would do it. Okay, so 425 C-ish. We want to show the limit as x goes to 3. Now I get to make up some stuff of, oh wow, really tricky. Woo. I'll put a 2 there. All right, so that limit should equal, the plug and chug version, so 9 minus 3, 6 should be 8. So we want to show that.
Can we not just use the fact that all polynomials are contiguous?
Well, that's a pretty damn good argument. But if we look at the that's, yes, like out in the wild, woolly world when you head out, that's a fucking brilliant argument. But it does require us to use definition 421, alas. Yeah, damn. Got me with the legal mumbo jumbo. So, all right. So what I would do is a little scratch work, and these actually aren't too bad. It shouldn't take too long to get these out. So the scratch work is, I know that I'm going to be dealing with f of x minus l and wanting that to be less than epsilon, right? And so I start here and work my way backwards to a target for x that will make this happen for an arbitrary epsilon greater than 0. So here we've got x squared minus x plus 2, and then there's one other thing I want to write here, minus 8. And I'm going to want that less than epsilon. And think about where we want to head, we need to get some kind of x minus 3 less than delta that implies this. So what I'm going to be looking for, Kayla, is I'm going to work this expression, I'm going to simplify it, and inside here I'm going to be searching for information about this quantity, x minus 3. Because that's really what it all relies on. So, once you do this part, you will always be able to find this in there, unless it's some kind of like transcendental function that just things are very weird about. So this actually turns into x squared minus x minus 6. And we all can see there's a beautiful factorization there, and it's not surprising that x minus 3 showed up, right? Yeah, so this, let me show you what I shouldn't do. Here's what I don't want to do, but it's kind of the right idea. I don't want to just do this. But it tips me off on how I might proceed here. Because I don't want this, I don't want delta to depend on the x value. It will, but I want delta to be a pure function of epsilon and not a function of x as well. So I have to pull out dependence on x in this argument. So, so let's go back a little bit. If I can understand something about x plus 2, life is going to be really good. So I'm going to put kind of here. Kind of need to replace x plus 2 absolute value with a constant. Or a constant bound. It's really constant bound is what I'm going to look for. So this is where I have to assume something about delta. And if you remember on my x cubed proof that I did, we said, all right, let's just assume delta's less than 1. And that's okay, because delta is going to be a small number in general. It's okay to set an upper bound on delta. Can't set a lower bound on delta. That's the problem that we want to avoid. So we're going to assume that delta is less than 1. Or we can say less than or equal to 1. What the hell? Why not? What would that mean? So if this is true, then x minus 3 less than delta would imply that x minus 3 is certainly less than 1. And now from here, I can get a bound on x. We've done this game before where I pull this into a double inequality. And so this is what I need to assume. If I assume delta is less than or equal to 1, I'm assuming this about x. That's really what I'm trying to say. So assume this requires this be true. Let's stop, make sure that makes sense. Kayla, you asked about this, so please let me know if that does make sense. Yeah?
Yeah.
Okay. So now I can actually understand something about this. Because I've got a bound on x, I can get a bound on this. Reconfigure this inequality into a statement about our friend x plus 2. So I'm going to add 2 to everything in there. So I got 4 is less than x plus 2 is less than 6. And that means that the absolute value of x plus 4 is less than 6. And it's also greater than 4. We could actually go that far, just to say that. I think I'm going to want to say that because I'm going to end up flipping x plus 2. And so to have a lower bound on it when I flip gives me an upper bound on the reciprocal. So this means that 1 over x plus 2, and this is a little bit different than I did it last time, but it's totally kosher, is less than a 4th and greater than a 6th. If delta is less than 1, and that's what we got. So with that assumption now, I can take let's call this inequality star. So star gives us x minus 3 is less than epsilon over x plus 2, which now we know is less than epsilon over 4. Make sure you see that. So look, do you see what I'm doing? I'm just literally multiplying through here by epsilon. And I get a bound on it. But I'm wanting that upper bound as well. And I'm going to put this here because there's a strong caveat here. Little note, just provided delta is less than 1. So now it looks like I'm getting my delta response right here. So this thing is going to be my delta response. But I gotta be careful because it's possible that epsilon, what if somebody gives you epsilon is 10? Well, then that's gonna make this bigger than 1, but we've already insisted that delta has to be less than 1. So what we're gonna do is we're gonna let delta equal the minimum of this quantity. And if that quantity is bigger than 1, we'll just cut things off at 1. So that, now we kind of just unravel this in the reverse direction, so that if x minus 3 is less than delta, it means it's less than both those quantities, we have x minus 3 has to be less than epsilon over 4. So make a note of that. And this sometimes, like even in my mind, and I've done this a billion times, I have to think about this and convince myself every single time that saying that x minus 3 is less than delta means it's definitely less than epsilon over 4, regardless of what epsilon over 4 is. See if you understand what I'm talking about in terms of the subtlety. Maybe it's easier on your mind than it is on mine, but this always implies that happens. And once that happens, I can unravel this whole chain back up this way. And it follows that. We could whip that back out. But I would actually include that as, you know how I always say put that off to the side? I think including that in your proof would actually be really helpful to the reader. And then you don't have to unravel it. You could just present that up front. Notice that. So let's not even say this. Notice that, just to get a nice proof. Notice this. And it follows from our previous observations that x squared minus x plus 2 minus 8 is less than epsilon. And that's oh, and since we're just doing limits here, I got to put that as well. And we should also put, sorry, one last thing. Let's keep that away from 0 as well. If this was a continuity proof, I could have x equals 3, but I'm not allowed to have x equals 3 in a limit statement. And so, you know, the limit thing is true. Does that help on how to proceed with that one?
Thank you.
Yeah, you're welcome. Let's talk about D really quickly, because it's a slightly different approach, but it's also kind of the same approach. So in D, we've got something like this. Let's see. So D-ish is going to look like this. We've got limit as x approaches 5 of 1 over x equals a fifth. So again, my scratch work is going to be the f of x minus the limit. Oh, yeah, and this will be nice. So what am I searching for? What am I trying to find out of here? This is going to be my epsilon thing. what am I going to be seeking in here? A statement about what? What's going to go in there? -5, right? Because yeah, that's the limit point. Yes, exactly. So we're seeking this inside here. So any suggestions on what I could do to this statement? Start manipulating my way there.
Does it make sense to take the reciprocal of everything? Can you do that?
Like, how do you mean?
Like divide everything by, or no.
By a third?
What am I trying to say? So like flip everything. So then it's x minus 5 is less than 1 over epsilon.
I don't think that's how order of operations.
Yeah, I think that would be befouled.
Okay.
So I think that what you're saying might be something like this, that 1/2 minus 1/3.
Yes, that's wrong. Okay.
Yeah. I don't even want to go. You got it. Yeah.
Yes.
But how could I get an x minus 5 out of this with legit, no, not that that's an illegit, well, it was illegit. With legit operations, how can I get x minus 5 in this?
You can multiply everything by x, and then.
Like on both sides?
Yeah.
Like, but, so now I've introduced an x over there. That looks dicey. That looks painful. Ooh, this is good. I'm gonna let you all sit on that for a minute. Don't get too complicated. Could you combine those fractions? How would you do it? How do I add fractions, real analysis, Math 454 students?
Yeah.
Yes. Common denominators, indeed. So, 5x would be a nice common denominator, and this one would get a 5 on top, and this one would get an x, right? And so now I'm starting to see x minus 5-ish things, good shit. This is in an absolute value. So this is actually the same thing as this. Thanks. Tossing out the sign, right? Don't care about it. So, this looks, so now, no, it looks like I'm starting to do the shit that I was harassing you about, but now now at least we got x minus 5 in here, right? So essentially, no, it's kind of what you were suggesting, except by instead of just multiplying through by x, I multiplied through by 5x, the absolute value of 5x. So I take back my chastising. So that could have worked, because you pretty much would have ended up here. Now what do I do? Like, this is horrible. It's still horrible.
It's kind of similar to what you did over there.
Yeah, what? What's
you just
that?
need to limit your delta.
Yeah, let's limit delta. So that there, it's already written. Great. Can you finish this up? Take a minute. Can you finish this up, please? Practice now. Enjoy later. Right? Is that heading there. Now we can actually get a bound on x that syncs with the delta part of our proof. Anybody got delta for me? Maybe no?
Maybe.
Maybe.
It
What do you
sounds
think?
wrong.
Just give me let's hear it.
30, the minimum of 30 sigma or 1.
30 epsilon. Yeah,
Epsilon.
perfect. Yeah, it doesn't. It's just a small Greek letter issue, but yeah, who gives a shit? That's it, man. I like it. Like you're just gonna start doing instead of this, you're gonna go with sigmas and like change everything.
I'm just gonna call that sigma though.
Okay, I like it. Yeah, perfect.
It's a dead letter. No one cares.
What? In our, I don't care. You're right. So minimum, right? Of because this. So check this out. What Noah's saying, and he's totally right on. I want information about 5x. So if I multiply through here by 5, I get 5x is less than or equal to 30. And so that's where he's getting the 30 from, that this quantity, if delta's less than 1, then this 5x must be less than 30. Right, that's it. So I'm gonna put 30 epsilon and 1. Now that looks weird, and I know why it feels weird, right? Because we're used to seeing epsilon over something, but if we were actually looking further away, like, well, actually, let's just look at the picture. So here's 1 over x, and we are looking at 5 out here. So let's see. This is 1/5. So if I pick up an epsilon window right here, look at how big the delta window will be, because that function is so flat, right? So we expect to have a lot of room to play with, and you've got this expansion going on just because of the shape of the graph. If we had done it over here, it would have been the exact thing. If we had done this at 1/5 over here, then your epsilon window requires a very small delta window. So, good job. Feels weird, but when we think about it, it all comes together. Kayla, does this help on how to
Yes.
roll with
thank
these?
you.
Cool. And everybody's clear, do not do B, please. And A should be pretty straightforward, I think. Right?
Yes.
Delta's epsilon over 3. Yeah, you got that? That's the answer for part A? Okay, cool. All right, any other questions? Kayla, you got any more? You good?
I don't think so.
You don't think so? Okay, wonderful. All right then, onward. My goodness. trying to remember where we ended up. We were talking about uniform continuity. And we started with an example of x cubed being not uniformly continuous on the reals, I believe. How far did I get after that? That was it? Okay. Cool. Okay. Great. Let's take a look at another example. One of my favorite functions. I don't know why it is, but it's just, there's something about it that's just so simple, and it's got a great shape to it, so well, that didn't get much better. So this function, and let's consider it as a function with domain of the reals, and when you sketch this thing out, I guess this is the part I like about it, the shape. I hope I don't have to buy another case of these black pens before the semester ends. I guess I need to get ready for the future, next fall, so forth. All right, so this function, this better be solid. Yeah, okay. So when x equals 0, the output is 1. As x goes to infinity, the function goes to 0 plus or minus infinity, and you've got this asymptotic behavior, and it looks a lot like a bell curve. I think that is what I like about it. Quite lovely. We could do Calc 1 and figure out the inflection points, right? We could do all sorts of cool things because we change from concave up to concave down. Where does that happen? Oh shit, I'm gonna do it. I just gotta know. I mean, sometimes you just gotta know, right? So this is x squared plus 1 to the negative 1. Let's differentiate. I'm gonna be doing some differentiation with this thing, so let's review. Right, we got that. And so literally f prime is negative 2x over x squared plus 1 quantity squared. And then f double prime. So you can see you have a critical value at x equals 0. Right? That is 0 at x equals 0. And that jives with what we know we've got here. That word I just said, I don't really know what I'm saying. So I don't know if that word is jives or jibes. Does anybody know? Or is that just such an old person word that no one knows? It's a V?
I think so.
Okay, cool, thanks.
Just
Jives.
like they dance together.
Like jive.
Yeah.
Okay. Oh, yeah. Okay, thanks. Yeah, that makes sense. So that jives with what we see here. And then the second derivative, let's see, so derivative of the top times the bottom left alone minus top left alone times the derivative of the bottom. Chain rule. Oh wait, let's put the chain out in the back. All over. X squared plus 1 to the 4th. And so I can factor, notice how each one of these has an x squared plus 1 in it. I could factor that out front, cancel it, so I can do this stuff with you all. I wouldn't do this. I would be more careful with my calc class. Let's see, so we'll have plus 8x squared. That's really cool, okay. Yep, this is all looking good, and then there'll just be 3 of these in the bottom. And then that top becomes 6x squared minus 2 over x squared plus 1 cubed. And you can see that you have zeros of this. So this equals 0 when x is plus or minus 1 over root 3. Yeah. So that's where our inflection points are. So completely useless to our goals, but sometimes you just gotta do what feels like it needs to happen. All right, fun. So anyway, onward. This function is uniformly continuous on R. So prove f is UC on R. Let's refresh our memory. Do you remember? Take one, I'll give you 1 minute. Can you recall the definition of uniform continuity? karma-free. That's a real smattering of applause. That's all right, can somebody give me this? Looks like you're all still writing. I better wait a minute. So you call your lifeline, and lifeline says, I'm pretty sure it starts with for all epsilon greater than 0. And you say, that doesn't help, I knew that. Because everything starts that way in this class. What's the next stuff?
There's one delta such that continuing on to define continuity.
Yes, such that,
Such
now
that
insert definition of,
x minus y is less than delta and f of x
Oh. yes,
or f of x minus f of y. Yes, yeah. For all x and y in set A.
in set A, but in
Less than
here,
30
yeah.
in R,
okay.
yeah.
Beautiful, nice, thank you. Indeed. So, remember, this is just continuity, and instead of a point C that we're talking about, it can be any point as the center. So that's why we replace it with Y. You could put a C in there, and it's okay, and then it looks just like the continuity definition. But this is also saying, no matter where we are, one delta suffices for all epsilons. You give me an epsilon, tell me where we're at, I don't care. I don't need to know where we're at because I just know epsilon and I can produce a delta. Because it won't depend on where I'm at in terms of the response. So, that's what we got to show. So scratch work, how does this work? Well, you start with this, and I hope if anything, you're kind of seeing just that a lot of these things, there's a lot of the same stuff happening over and over again, right? It really is. The scratch work is almost always the same. You start with your conclusion, work back to get something that reveals info about the hypothesis. So, what would this look like? Well, that would be 1 over 1 plus x squared minus 1 over 1 plus y squared. And let's just kind of, so we're going to want that. So let's explore this quantity, get a common denominator. We're like super good at that now. And then on top, what are we gonna have? So we're gonna get x squared minus y squared. And I'm abusing, I'm not abusing, I'm luxuriating in the absolute value, because it allows me to flip orders on subtraction to make them aesthetically pleasing to myself. So yeah, What do we need to find info about?
What delta is equal to?
What?
We need to find delta?
We need to find delta. What is delta? What is delta revolve around? Bless you.
Epsilon.
X minus y. So how can I get x minus y out of this? Do we see? Ashley, you see it. I see you see it.
I see.
Tell me what to do. It's just your idea. How could I get x minus y out of that top? Exactly, beautiful, thank you. Just difference of two squares, right? So we see on top that this is going to be, so check it out. I'm actually gonna pull the stuff that doesn't involve x minus y into, I'm gonna group it, So what would it be cool to have a bound on?
All that.
Exactly, exactly. If I only knew that this maxed out at some value, no matter what x and y are, I could go, oh, hey, this is less than or equal to that value, and holy shit, I've got my epsilon delta relationship all set up, ready for this m. But I first have to convince myself, and then my audience, that this is bounded. Let's see, you all had Calc 3? That's Calc 3, right? How do we do that? How do I optimize? Wait, this class doesn't have Calc 3 as a prereq? It has all your math as a prereq. Everything you've ever learned except algebra. Except abstract algebra. So let's look at this quantity without the absolute value, because that definitely feels less intimidating. Let's call that g equals that. What do I do, friends? How do I optimize a multivariate function?
You take the derivative with respect to x and then respect to y.
Beautiful, yeah. Take some derivatives for sure, right? So first thing is I find, so if this is g, I find first partial with respect to x. I think I did this. So I'll save us some suffering. It turns into 1 minus x squared over 1 plus x squared squared, 1 plus y squared squared. And then the partial with respect to y is 1 minus y squared over 1 plus x squared squared, 1 plus y squared squared. What are my critical values? Because I'm going to set these equal, just like Noah said, we're going to, wow, this pen is just not good. Set that equal to 0. What's the solution? Get Desmos up for us. Not to answer that question, but it's totally cop out on the second half of it. We'll be here a long time if we have to go into the second order tests for Calc 3. You can shout it out at any time. What are the critical values? Hint, there's 4 of them. Good time for a bathroom break. Computer's warming up, you guys are working. first person who didn't get all that applause. Come on. CVs? What would those be?
Any point where x and y is plus or minus 1.
Yeah.
So 1, 1, negative 1, negative 1.
Beautiful.
The rest of them.
Yeah, exactly. So, I mean, the top is dead when x is plus or minus 1, top is dead here, y is plus or minus 1, that's 4 combos, you got 2 pairs of socks, you got 2 pairs of pants, you got 4 outfits, so forth. So we've got these CVs. And if we were in Calc 2, what would we do next? But we're not going to, because it'll be like just the rest of our lives if we have to do it.
We would check if there's saddle points, local maxes, or local mins.
Beautiful. So there's this thing called the discriminant, right? So we would continue on. Yeah, is that
I do
remember?
not remember what the discriminant is. I just remember it exists.
That's a different one. But
Oh,
boy,
that's
that's
different, but
hella
that's
good.
old. I just, yeah.
Yeah, yeah,
I did
yeah, no.
something with it yesterday, so.
Oh, cool, cool, cool. Yes, yes.
Fresh
For
memory.
quadratics, that is
Yeah.
quite a beautiful.
Fresh in my mind.
Crank that out, and then wait, is there a 4 in there? I don't think there's a 4. No,
Not
because
in
this
that one.
not in this
Yeah.
one, yeah. Because this is actually the determinant of a thing called the Hessian, and you probably don't learn this in Calc 3, but when you study multivariate things, this thing called the Hessian is really the generalized second derivative. It's this, and it's that determinant. So that determinant, you will notice, is not at all what I actually just wrote over here. Put a minus there and a plus there. So I'm glad I checked that out, because this determinant is that times that minus that squared. And so it should have been the other way around. Yep, yep. So anyway, we would plug these points into here, and then if this thing was negative, I had a saddle point. If this thing was positive, I then had to check the sign of the second partial with respect to x, right? So none of this is going to matter for anything you're about to do in here, but if d is greater than 0 and fxx is greater than 0, then we have a local min. If d is greater than 0 and fxx is negative, we have a local max. If d is less than 0, we have a saddle. If d equals 0, you're screwed. You just gotta figure out something else. You gotta do what I'm about to do, which is summon Desmos to look at the damn graph. Let's get real, folks. You're out in the world. You're in your workplace. I've been watching some TikToks on people talking about tech jobs, and just like no matter where you are, no matter how much training you have, you still end up Googling how to do things. So we're in good company.
I think
here.
that's true to life to any job.
What's
I
that?
think that's true to life to any job.
I think you're
You're
right.
a surgeon, you just gotta, where is the spleen?
Yes, exactly. Exactly. So we're gonna. Desmos doesn't do 3D graphs, does it?
GeoGebra does.
Oh, okay. It's GeoGebra. Okay, thank you. GeoGebra.
GeoGebro?
GeoGebra. Okay, let's see. Is this just the calculator, maybe?
I think you gotta look up 3D.
I think you're right. There we go. Good call. Oh, thank you. Really on it. So let's see, we got x minus y. Oop, how about some parens? X minus y. this is just soothing, like just watching that unravel, right, before our eyes is freaking amazing. Okay, I think we've got our answer here. This point right there, here, let's just get a top view. You see this is 1, 1 here? Yeah, and you can see you've only got one bump, and 1, 1, I'm pretty sure I'm reading that right. Is the local max, I think, right? It's not, this isn't great. This isn't great.
You put x minus 1, y minus 1, 1, or no, never mind.
Okay, everything seems
I was
okay.
thinking you could do a trace, but I don't remember how.
Oh, okay. Oh, I see what you're saying. I just wanted to make sure those coordinates, oh, there we go. So that's 1, 1, that is 1, 1 where that peak is. And -1, -1 where that trough is. So there we go, it's proved. That doesn't cut it in Calc 3, but it cuts it for us. So we have a max at 1, 1. Wait, how could, no, that can't be because it's 0, right? It's 0 at 1, 1, and that's, am I reading those coordinates wrong? Yes, I am. You okay, so it makes sense that it would be x is 1 and y is -1, right? So that's it. So these opposite points are, oh, and it's actually a little bit more visible. Yeah, that's -1, that's 1. So, okay, leave that up. But long story, not short. Could be longer, I guess. That's all I'll say. Is that the max? Thank you. Oh my God, you're amazing. So this is our max, and this is where our min occurs. And so the max value. So this evaluated at the point 1. Wait, it is x. Oh shit! I entered the wrong function. I put in x minus y. It's x plus y. Okay. No, it's like,
Do you want to
no, I'm just gonna cop out and go. Okay, it's a lot the same, and this is actually, yeah, that's garbage. These are saddles. These are saddles, and so this is my max, and this is my min, and that's why that looked fried. So this max is at when we've got 2 on top and 4 on the bottom. 1/2. Yay, holy shit. So this, for all xy in the entire plane, is less than 1/2. Less than or equal to 1/2. My God. So look, let's summarize what we've got. That was the scratch work. That was the scratch work. So, thus, f of x minus f of y is less than or equal to, because that's what this quantity was. This was f of x minus f of y, less than or equal to 1/2 times x minus y. So check this out, this is really neat. In fact, this is a much stronger thing than uniform continuity. This, and so this is for all x, y, and r. This quantity is actually called Lipschitz, which is, giggle-worthy if you're not grown up inside, and I'm not. So, and I never was. And so this is Lipschitz. A Lipschitz function means that there exists an m that's positive such that f of x minus f of y is less than or equal to m x minus y. That gets you uniform continuity, but uniform continuity doesn't necessarily imply that, but here it totally does. So this is Lipschitz. There exists this m. The good news is once you've got Lipschitzness, once you've got Lipschititude, you've got an easy relationship, because now, look at this. If you take this, oh my God, I don't know what I'm gonna do for calc. These pens dying so much. But to get that less than epsilon, all you have to do is set x minus y less than epsilon over m. So this becomes your delta right here. So for our function, let delta equal epsilon over a half, i.e. 2 epsilon. And then we have when x minus y, so that x minus y less than delta means x minus y is less than 2 epsilon, means that this whole thing is less than epsilon. And then that gets us our appropriate response. It implies fx minus fy less than epsilon. I'm gonna make you do something. I'm gonna make you do something before we leave. We got 15 minutes, we cannot. Oh no, I'm not. I'm not gonna make you do something. I'm gonna prove a result and call it a day, but man, do I wish I had new pens.
Do not provide pens?
What's that?
Do not provide pens?
They do provide pens, they provide garbage pens that I hate. And they, the other colors don't show up on my recordings. So I need like a vibrant, just the best black I can get. And this, oh, yes, score. Ready. All right, last uniform continuity thing for the day. I'm sorry, but it is. Just have to go learn about it on your own after this. So, get some space and approve a little result that makes life super easy. Because man, this is a pain in the ass, right? Like having to always produce the delta epsilon relationship and do all this stuff and this optimization, that is brutal. So wouldn't it be nice if we had a nice theorem that said, if this happens and this happens, you got a uniformly continuous function, and we have such a thing. It is theorem 447. Theorem 447 says that if a function f from some set A into R is continuous and A is compact. Probably should have called it K just to like really, set things up nice. A is compact, then F is UC on A. What is it? So we're going to proceed by contradiction. And what that means we're going to assume F is continuous on A is compact, but that F is not uniformly continuous on that set. How do we show something's not UC? Remember, we took the definition of it on Monday and we negated it and then twisted it a little bit. Do you recall how that worked? What exists as that? gosh. There's a man who's been awake this semester. What else? What else exists? What? In two sequences, x sub n and y sub n, sequences in A, such that, let me help out here. When we pair the terms up, they're getting closer and closer together. And let's use that epsilon naught we got from our friend Noah. And f of x sub n minus f of y sub n is bounded away from 0 by that epsilon, that fixed epsilon. So we can't get, we've got a series of points that are basically kind of going to the same place, but the function value is being bounded away from 0. So these two things aren't converging together, even though these seem to be. And this is really general, right? These sequences, remember what we used last time when we were showing x cubed, wasn't? We had, these sequences don't have to converge. We use these two sequences, neither of which converges, but their difference shrinks to 0 as n goes to infinity. So notice these sequences do not have to converge. They simply have to get closer and closer together. It's almost like a Cauchy-ish kind of thing. So just want to point that out. All right, okay. So I've got all this stuff. Because I'm assuming f is not UC, I've got this epsilon naught, and I've got these two sequences that work just beautifully. But I also know A is compact. So realize these are sequences in A. But also, A is compact. So what does that mean about this one of these sequences? So I've got this sequence x sub n, so since, let me get you set up here, x sub n is a sequence in A, and A is compact, what can I say?
That it converges to some limit point in A.
Yeah, yeah, really nice. We just got to toss subsequence in there. So compactness means you take any sequence in the set, it has a convergent subsequence that converges in the set. Nice, Kayla. So since that, there exists an x sub n sub j in A, such that x sub n sub j converges to some x that is in A. Lovely convergent subsequence. So this is something really neat. This is a really neat, we've got these two sequences that are kind of in lockstep together. What am I doing? Right, you can pair up their terms. So what we're going to do, since we've got a subsequence of x that converges somewhere, let's say it's like this, say that's like x sub n1, and then maybe this is x sub n2, and then, let's do another one here, just so that you can see what I'm doing. I thought about this picture this morning, it seemed like a really good idea. We'll see, and then let's say maybe that's x sub n3, right there. So those are terms from the x sequence that are part of the convergent subsequence. I'm just saying suppose this was the case. I don't know what terms it's going to be, but just suppose. What I'm going to do is I'm going to produce a subsequence from y by just grabbing the companion terms out of y. So here I'm going to grab that. So that's going to be y sub n1, and then this is going to be y sub n2. This is going to be y sub n3. Does that make sense? Yeah? Okay, cool. So, create a subsequence from y sub n by grabbing corresponding the corresponding terms I took this to end the sentence there. So i.e. we've got the subsequence y sub n sub j, and we're just going to grab the same indices. I hope that makes sense. So now it seems like the y, since the x terms are getting closer to the y terms and the x terms are converging, sure seems like this should converge to x. Seems like. Let's prove it. So notice that. And here's another game you've learned quite well this semester. So notice that y sub n sub j equals y sub n sub j plus, no, sorry, x sub n sub j.
Yeah, I was like, what?
Yeah. Plus y sub n sub j minus x sub n sub j. So the game where I just add on 0, right? I'm just they're doing that game again. What is happening to these as j goes to infinity? What's happening to that difference? Goes to 0 by hypothesis, right? So this goes to 0 by hypothesis. And this goes to x as j goes to infinity. And so by the algebraic limit theorem, limit of the sums is the sum of the limits. And so this means y sub n sub j must converge to x as well. We're almost done. So now we've got, let's come back to f of x sub n sub j minus f of y sub n sub j. Bless you. This is the thing. This should be bounded away from 0 by, this can't be less than epsilon naught by our hypothesis. But what is happening? How do I know that as j goes to infinity, this converges to f of x minus f of x? Why do I know that? What assumption in our hypotheses allows me to say that? Because.
So, the thing we just did, right?
But how do I know that so we know that the things inside the functions are converging to x. How do I know that I can bring the limit inside? So in other words, how do I know that the limit as j goes to infinity of f of x sub n sub j equals f of x? That's what I'm asking. So how do I know that? We didn't quite address that yet, Noah. What assumptions do we have? It's actually gone off the board. Continuous, yes. So by continuity. So this, because f is continuous, exactly. That means you can bring the limit inside of the function. That's continuity. That's a nice way to think of continuity, that you can bring limits inside as the argument of the function and get the same result. So, I mean, this is literally plug and chug. This right here is just like plug and chug because it's continuous, so it's all good. And this looks dead. So since that limit is shrinking to 0, this contradicts the assumption that this f of x sub n sub j minus f of y sub n sub j can't be less than epsilon naught. Because if that's going to 0, eventually I could shrink below any bound. Right? I could get less than any epsilon. So that's a contradiction. What caused the problem? This. The assumption that f was not UC. That's what allowed us to build these sequences. Thus, F must be uniformly continuous on A. And before you leave, in just the last 2 seconds, I want to show you an interesting way to do this that we could do just really quickly. So here I've got a nice compact A here. And what I could do is that since F is continuous for each X in here, so I fixed some epsilon greater than 0, and up here I pick a bunch of V epsilons around each image point, and I cover the image of F of A with these guys here. So for each X in A, choose a V epsilon neighborhood around it. By continuity, for each one of these, you can pick a delta neighborhood down here. I'm saying this is super shitty, so and if you don't get it, it's totally cool. But I'm gonna do this for all of these, and in the process, I'm gonna end up covering the image of F of A with these V, and that's the hint right there, the covering term. I'm gonna cover this with epsilon neighborhoods, and the corresponding delta neighborhoods will cover this down here. Because A is compact, I can take that open covering and produce a finite open covering of it, a finite subcover. And once I've got a finite subcover down here, I've just got a bunch of V delta 1, X1, comma, up to V delta sub n, X sub n down here. And now I can find the minimum delta out of this collection, and that one delta will work for all these up here, and that's the rough, super shitty version of the proof. But open coverings are a cool way to approach it. Thank you very much, my friends. Thank you. We'll see you on Monday. I'll have your papers back on Monday too. Oh God, and I think I have your papers that I never did give back.